Okay, so today we're going to answer question number 4 and number 5 from Grant Sanderson's really neat video about the sphere. So the first thing we've looked at in our little video series is you have these stripes and they get projected down. Do you remember what the circumference of that stripe was?
I think it was 2 pi r cosine theta.
Theta was from up here. So theta was measured this way. So could this be 2 pi r cosine theta?
The circumference?
Yeah.
Yeah, because the radius up here was, remember, was r. It was sine theta.
Okay, why? Why is it sine?
Because you've got r is going this way, r is this, theta is this, the radius is here. And the definition of sine theta is this over sine theta is this.
Yeah. So from definitions you can see that it's sine. But why can you just sort of look at this and know that, like when you're up here, the radius is not r cosine of theta?
Because that would be big.
That'd be big.
And it's small.
R sine theta. What was the area of this strip approximately?
It was approximately 2 pi r sine theta times d theta, which is our thickness.
Yeah, so what was it again?
It was 2 pi times r squared sine theta d theta.
Okay, and why was this?
Because the thickness was approximately r d theta.
It was r d theta.
You multiply circumference with the thickness, and you get approximately the area.
And then when we projected this down, we got a ring down here. It's going to be hard for me to draw, but a little ring. And what was its area?
That area was, I believe that was 2 pi r squared sine theta cosine theta d theta.
Okay, and this had half the area of what ring?
It was the ring that had a theta value of twice the original ring.
Okay, and why does that happen?
Because of how sine of 2 theta works. The sine of 2 theta is 2 sine theta cosine theta.
Okay, so the 2 theta part eats that too, and the sine and cosine, and it gets us up here, and then we're missing that too, so that's why we get the half. So we get another ring down here. So question number 4 in Grant's video says, and I'm just scrolling forward to it in the video right now. Sorry. Question number 4 is, explain how the shadows relate to every other ring on the sphere.
Alright.
So why do these shadows relate to every other ring on the sphere?
Well, because you're going from theta to 2 theta.
Okay.
And you really actually have 2 of these shadow disks. You've got one from the top and one from the bottom.
Okay.
So from the top, from theta goes from 0 to pi over 2, or 90 degrees. I think we're using degrees here. But
Well, we're using radians.
So all the rings shadows go into this, and then each shadow goes to every other ring because the theta value is multiplied by 2.
Okay. Nice. And why were you saying that this shadow corresponds to 2 rings?
Well, because that's just from the top hemisphere. From the bottom hemisphere, you get the same shadow disk and the same correspondence on the bottom.
Okay. All right. So, and then question 5 is, why does that imply, since we relate to every other ring, that the shadow is 1/4 of the surface area?
Well, so the area of this disk is just pi r squared.
Okay. So the area of the disk is pi r squared.
And you know that pi r squared relates to half of the disks on one hemisphere.
Okay.
So pi r squared relates to 1/4 of the circle.
1/4.
Or sphere, the sphere. And then, so 4 pi r squared, 4 of those disks would relate to the entire circle, or sphere.
Half the disks on one
Hemisphere.
hemisphere. tripod there. So pi r squared, this has half the area. The area of these discs are half the area of half the sphere. Okay?
A quarter of the area.
Yeah, I wouldn't say it's half the disc on one hemisphere because it was every other disc,
Yeah.
so they do come down here. So instead of saying half the discs on a hemisphere,
So it's half the discs. I guess on the full circle. But you're counting each one of them twice. Because each one is mapping to 2 discs.
okay, all right. So half the discs on what?
It's half the discs on the circle, on the full sphere, but twice.
Okay, yeah, that works. So half the discs on the sphere, and then you're right, and you count them twice. 4 pi r squared. Pretty good. It's a good problem. Good work, Hunter.